Alright, so we have now an idea what is the energy of the system. Now let us suppose we do a transformation at constant volume. Now this experiment is known as Joule's experiment. It is another experiment carried out by James Prescott Joule. So what he asked is, if we do a transformation, how the energy or internal energy of the system changes. So let us now define the first law more formally. So here we say that if a system is subjected to any cyclic transformation, the work produced in the surrounding will be the heat withdrawn from the surrounding, and that is how we formulated the first law, that D cross Q in the cyclic process will be D cross W. We are keeping a negative sign just to make sure that the convention is correct, and then by adding them we got du for any cyclic process is 0, which we stated in a different words that energy is a state function unlike heat and work. Now remember, here we gave an example of single step expansion followed by single step compression, and we know that the work done is very different. However, we said that work done, which is the net work done by the surrounding, was utilized in raising the temperature of the surrounding. Now you may ask this question, if we had done it in a reversible way, meaning changing the pressure of the system infinitesimal amount, changing the pressure of the system by infinitesimal amount, that will lead to the area under the curve same for the forward process as well as in the backward process. In this case, these two areas cancel each other. So if I write W in the first step and W in the second step, that will be perfectly 0. So in this particular case, D cross W is equal to 0, D cross Q also is equal to 0 for the cyclic process. For a reversible cyclic process, then we can write, for any reversible process, is nothing but equal to 0. But remember that this is not always true for any not a reversible process, which we will call as irreversible process. This integral is non-zero. However, their addition must be 0. Now let us move on and ask this question, what happens if we do a transformation to the system at constant volume? Again, Joule did a very excellent experiment where he tried to understand how this quantity, which we just defined as the difference between work done and heat withdrawn, which we called as the internal energy of the system, changes by change in volume as we make the transformation. So for that, mathematically we can write the internal energy as a function of volume and temperature. Now, which means the total differential du can be written as a partial differential first with respect to volume, keeping the temperature constant, and then taking the partial differential with respect to temperature, keeping the volume constant. Now, this comes from just the fact of differential and partial differential, the calculus which you learnt in 12th standard. If suppose z is a function of x and y, and if I ask this question, there is a transformation dz which is the total differential of z, and if I ask this question, how much part of dz actually is caused by changing in x alone, the answer will be I have to take the partial derivative with respect to x, keeping y constant. So, we are not changing y, and then multiply it by the change in dx. So, that will be the part which we sometimes write as dz(x), and then similarly there will be a part which is dzy, change in this differential dz due to the change in y alone. In this case, we keep the x fixed. Now, we have used the similar formula here. Now, Joule asked this question that how one can measure this quantity. We will come back to it. Before that, let us do some mathematical tricks. We already know from first law that du is d cross w plus dq, and d cross w we know that it is nothing but opposing pressure into dv plus d cross w. Now, if we consider a constant volume process, dv must be 0. So, du is nothing but dq for constant volume. So, we can use this equation for a constant volume process. Du is dqv, which is del u del t v dt. Now, we got a very interesting situation. If we divide dqv by dt, we get the heat capacity at constant volume, because remember that is the definition of heat capacity, how much heat is changed if we raise the temperature by say 1 degree at constant volume. So, that quantity is given by this partial derivative, which is del u del t v. So, we can rewrite the total differential which we just wrote for du as du is nothing but del u del v t dv plus cv dt. Now, our task is to understand what is this quantity del u del v t dv. So, that is why Joule did a very nice experiment to quantify this quantity. Now, what Joule did, he took a bucket of water, and then inside the bucket he kept two containers which are round bottom flask like, and with a stopcock in between. Initially, suppose there I am labeling them as A and B. Initially, some gas filled the container, but the container B was empty, and he was also used this entire system, which is just two bulbs connected by a stopcock immersed in a water, where the temperature of the water can be monitored by a thermometer, and there was also an stirrer In this case, the stirrer actually just rotates in order to maintain the thermal equilibrium of the system. Now, when the stopcock was open, the question Joule asked is what is the associated change in the internal energy. Now, remember, we will just use the same notation. Here d cross q, or the work done, is opposing pressure into dV. However, remember, when the gas expanded, the opposing pressure was 0, because initially there was no gas in B. So, you can think that when the boundary of this gas changes, when the gas tries to fill in the other container, always this boundary feels no opposing pressure, which means that P opposing was 0 in this case, and the work done will be nothing but 0. So, now from the first law we can write du, which was del u del v t dv plus del u del t v dt, which is nothing but d cross q plus d cross w, but we just said that the d cross w is 0 in this case. The d cross q was also 0 because Joule observed no rise in temperature. Since delta T was 0, d cross q also has to be 0. So, the right hand side of this equation is 0. Now, since delta T was 0, which means dt was also 0, which means this term del u del v t must be 0 since dv is non-zero. So, Joule said that del u del v t is 0 according to his measurement. We will come back to it when we discuss the Joule-Thomson experiment. Now, before we switch to other topics, let us briefly discuss what is meant by this, why del u del v t is 0 for an ideal gas. Now, let us have an analogy with our particle in a box model, which we learned in quantum mechanics. Now, you know that as the length of the box changes, the energy levels also changes. So, from that perspective, del u del v t should be non-zero because it should be dependent on volume. However, remember that this associated change in energy is already accounted for. Why? Because we already discussed that when work is done on the system or work is done by the system, there is a change in pressure. That pressure is proportional to the square root of temperature, which is actually related to the supply of energy. So, the energy we are talking about in this context is not the kinetic energy, it is the internal energy of the system. Now, let us consider another process in a similar way where we would like to keep the pressure of the system constant. As before, we will start with writing the energy as a function of, instead of volume and temperature, this time we will write it as a function of pressure and temperature. So, the total differential as before can be written as a differential with respect to pressure keeping the temperature constant multiplied by the finite change in differential change in pressure, and then a partial derivative with respect to temperature keeping the pressure constant multiplied by the finite change, differential change in temperature dt. Now, similarly as before, we will consider a constant pressure process. So, let us write the internal energy using the first law as dq plus dw. In this case, remember, we are considering a constant pressure process. So, I am just using a suffix p here. du is d cross qp plus d cross w, where d cross qp is the heat change associated with constant pressure process. Now, if we ask this question, what will be the total differential going from say state 1 to 2, we have to integrate over each term. And remember also that in this case the work done is nothing but minus P opposing into dV, but here the opposing pressure will be nothing but the pressure of the system itself, because it is a constant pressure process. So, throughout the transformation the pressure was kept constant. So, since pressure was constant during the change, we can also keep it outside the integral. So, in the next step we will just write it as Qp. Remember that we cannot write delta Qp because Q is a path function, and the second integral is nothing but V2 minus V1. Now, on the left hand side I have a change in internal energy, which we could write as U2 minus U1, and then I have here the constant heat change at constant pressure minus I have P into V2 minus P into V1. Now, we can organize this in a slightly different fashion. We can write it as U2 plus P2 V2 minus U2 U1 plus P1 V1 is equal to Qp. Now, in this case P1 is the initial pressure, P2 is the final pressure. However, P1 is nothing but equal to P because the pressure was constant. The P2 is also nothing but equal to P because the pressure is constant. Just to maintain the equations similar looking, I am using instead of P, P2 and P1, but the magnitude of P2 and P1 are equal to P. So, we can define a new term which is H2 and H1, where H is nothing but the U plus PV. Now, we see that this difference H2 minus H1 is equivalent to the heat change at constant pressure, where H is defined as a quantity equivalent to U, the internal energy, plus pressure times volume. So, the change in H now is equivalent to the associated heat change at constant pressure, and H, this quantity we call as enthalpy. Now, note that this enthalpy must be a state function, because we could write it as difference of H at two different states. H1 corresponds to the enthalpy of the system when the system was in state 1, and H2 corresponds to the enthalpy of the system when the system was in state 2. So, since we could write it as H2 minus H1, or a difference of the physical quantity at state 2 minus state 1, H must be a state function, it is not a path function. So, we got an interesting result where we say that change in enthalpy of the system is nothing but the equivalent to the heat change at constant pressure. Now, we will frequently use this concept, but before that let us also discuss. So, we just defined enthalpy H as U plus PV. Now, if we take the differential or the total differential of enthalpy, it must be equivalent to delta U plus P delta V plus V delta P. This is using the chain rule of differentiation. Now, remember that this is equivalent to QP or heat change at constant pressure. Now, since this is equivalent to heat change at constant pressure, when we write delta H, we will write for a constant pressure process, we can actually drop this term. So, we can write delta U plus P delta V is nothing but Q P. Now, let us try to understand what is the how a change in state at constant pressure happens. Now, as before, where we wrote as U as a function of volume and temperature, in this case we will write the newly defined quantity enthalpy as a function of pressure and temperature, and then compare the total derivative and write it in terms of the partial derivatives. So, here dH is nothing but the partial derivative with respect to temperature plus partial derivative with respect to, we first write the H as a function of pressure and temperature. So, the total derivative is the partial derivative with respect to pressure keeping temperature constant multiplied by the differential change in pressure plus the partial derivative taken with respect to temperature keeping the pressure constant multiplied by the differential change in temperature. Now, as before, we are considering a constant pressure process, and then you can easily figure out that at constant pressure this term goes to 0, and then we know that dH at constant pressure is nothing but d cross q p, and then we divide, if we divide both sides by dt, then we get del H del T P is nothing but d cross q p by dt. Now, this quantity is nothing but heat change per unit rise in temperature when the process is carried out at constant pressure, which means this is nothing but the heat capacity at constant pressure. Now, this definition of heat capacity can be used in the original equation, where we can now write the total derivative for any process where the pressure might be constant. Now, let us consider a process where we keep the pressure to be constant. So, just like before, we wrote the internal energy as a function of volume and temperature, and then wrote the total derivative du in terms of the partial derivatives. In this case, we will write the enthalpy as a function of volume and pressure and temperature, and then write the partial derivative in total derivative of H as the partial derivative taken with respect to pressure keeping the temperature constant plus the partial derivative taken with respect to temperature keeping the pressure constant. Now, as before, if we consider a constant pressure process, then dP is 0. In that case, only at constant pressure process we know dH is nothing but dQp, which is del H del T P dt. So, from that we can easily see that this quantity del H del T P is nothing but I should use d cross q p by dt, which is nothing but heat capacity at constant pressure. So, we can use this relation in the original equation and write dH is nothing but Cp dt, which is coming from the second term here, and the other term which is del H del P T dP. So, remember this has a very nice analogy which we just got in the earlier case. du is Cv dt plus del u del V T dV. By Joule's experiment, we saw that this term is 0, and we also argued that for ideal gas, since it was 0, since Joule showed that it is 0, we saw from Joule's experiment, in the earlier case we saw from Joule's experiment that del u del V T is 0. Now, the question is, what is the value of del H del P T? For that, we will discuss an experiment which is known as Joule-Thomson experiment. But before that, we will discuss the relationship between these two quantities, which is Cp and Cv, which are heat capacities at constant pressure and heat capacity at constant volume.